In this video, we are going to explain three main concepts of physics, which are 32.4, 32.5, 32.6 from the reference survey Jowett 9th edition. 32.4 is the mutual induction, 32.5 is the LC oscillation, and 32.6 is the RLC circuit. And now we will start with the 32.4 mutual induction. Mutual induction is one of the applications of Faraday rules. Faraday rule says that induced EMF equal negative N delta phi over delta T. N is the number of turns of the coil, delta phi over delta T is the magnetic flux change. And it was done by a magnet and a coil. But here it happens between two coils. The first coil, which has a current in it, we will call the primary coil. The second one, which hasn't a current in it, we will call the secondary coil. By moving the first coil inside the secondary coil, a magnetic field variation happens and the mutual induction results in. So we can say that the magnetic flux is directly proportional with the current that runs inside the primary coil. So the rate of change of the magnetic flux is directly proportional with the current, the rate of change of the primary current. And as we know that the induced EMF is directly proportional with the rate of change of the magnetic flux, so it's also directly proportional with the delta of or the rate of change of the primary current. EMF, so we can say that the induced EMF equal some constant times the rate of change of the primary current, and this constant we will call M, which is the coefficient of mutual induction or the mutual inductance. And its unit we can take from the law, which will equal volt times seconds over ampere. Volt times second, we can say it's called a Weber, so we can say that it equals Weber over ampere, and it also and the volt over ampere is equal ohm, so we can say that it's equal ohm times second. And all of this is equal to some unit that is called Henry, which is a scientist that discovered this coefficient. M, we can say that M is the link or the sensitivity between the two coils, and it is the induced EMF in the secondary coil due to a change in a current in the primary coil by 1 ampere in 1 second. M is also affected by some factors, which are the distance between the two coils, number of turns, volume of the coil, and core permeability, and we will discuss them now. The distance between the coil, as we increase the distance between the two coils, the sensitivity between or the link between the two coils will decrease, so it's inversely proportional with the distance. Also, the number of turns of the coils. Both of the coils is directly proportional with the M. The number of turns of both of the coils is directly proportional with M. As the number of turns of the first primary coil, if we increased it, more current will run in it, so more magnetic field will result. So more mutual induction will result. And also, if we increase the number of turns of the secondary coil, it will have more capability to result a more mutual induction current. And the volume of the coil is directly proportional with the secondary and inversely proportional with the primary coil. Why? It's directly proportional with the secondary coil, as if we increase the volume of the secondary coil, it will have the capability to collect more and more magnetic field. And also is inversely proportional, as if we decrease the volume of the primary coil, it will result a magnetic field in a small area, so it will be easier to be collected. And also the last one is the core permeability. As if we put a core between the two coils to increase the mutual induction between them, the core permeability to the current is directly proportional with the M. As if we put an iron core or also a copper core which has a high permeability, it will increase the M. And now with the LC oscillation. If you connected a charged capacitor across an inductor, you will see an energy exchange take place between the two elements. But why don't any of these elements store the energy and become settled? Let's see. The capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning and then the curve or the current flow will reduce. However, this will not happen in practice. An inductor develops EMF across it based on the change or the charge in the current flow. This means that a drastic change in the current is not possible across the inductor. Now the current flow starts from zero and increases to the maximum and then comes up to zero again. The current flow in the LC circuit is shaped like a sine curve. In the next 1/4 of time period, the current of the capacitor starts to decrease, resulting in another change in current. At the end of the capacitor discharge, if you check the EMF through or across the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. This also means that the current flow will be in the reverse direction for the next half of period. In an inductor or in an ideal LC circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillation of energy. However, practically, we can never achieve such an ideal behavior due to the presence of resistance. The resistance causes energy to decrease or to decay in the form of heat. So the oscillations will die eventually. As we increase the resistance, the oscillations will die quicker. And now with our last part in our video, which is the RLC circuit. An RLC circuit is an electrical circuit consisting of a resistor, an inductor, and a capacitor, connected in a series or a parallel connection. But in our case, we will only discuss the series connection. The name of the circuit is derived from the letters that are used to denote the constituent components of this circuit, where the sequence of the components may vary from RLC. The circuit forms a harmonic oscillator for current and resonates in a manner similar to an LC circuit, introducing the resistor increasing the decay of these oscillations, which is also known as damping. The resistor also reduces the peak resonant frequency. Some resistance is unavoidable even if a resistor is not specifically included as a component. RLC circuits have many applications as oscillator circuits. Radio receivers and television sets use them for tuning to select a narrow frequency range from ambient radio waves. In the RLC circuit, we need to calculate two main things, which are the impedance and the intensity. As shown here in the first figure, the intensity is in the same direction with the VR, which is the voltage in the resistance, and it's perpendicular to the VL, which is the voltage in the inductor, and also it's leading it. And it's perpendicular also with the VC, which is the voltage in the capacitor, but it's lagging it. Okay, to calculate, to add these three values, we can't add them algebraically. We need to add them in the way of the vectors. As shown here, in the right one, the XL is perpendicular to the R, which has the same direction with the I, and also is perpendicular, and the XC is also perpendicular to the R, which is but in the opposite direction. XC and XL have the opposite direction, so we can subtract them to give us the left figure. Here the XL minus XC is perpendicular to the R, which has the same direction with the I, and its summation, their summation is Z, which is the impedance. Back to the law, so the impedance here will equal to the from Pythagoras will equal to square root to the R squared plus XL minus XC squared. To calculate the intensity, we will use the same technique as shown here in the second figure by using the vectors to add the VR and the VL minus VC, and it will give us the Vmax. Vmax here, which we used in our rule, so the intensity will equal to the Vmax over the Z, which is the impedance, which is the total resistance in our circuit. And that was all for today. I hope I have succeeded in my explanation, and goodbye.